Hello, good morning, good evening, everybody. Welcome to MLDA's workshop. Today we'll be talking about ROS. My name is Sean, and I'll be the instructor for tonight. Okay, I'm passing my time over to Andrew first to talk about what we do here in MLDA. Andrew, please.
So wait, uh, yeah, hi guys. Hi, I'm Andrew. I'm the head of academics at MLDA. What is MLDA? So MLDA at EEE is a student-centric lab which aims to provide a platform to empower our EEE or IEM students learning and deploying of ML and machine learning and data analytics skills and knowledge in both the academia and industry. We do so through our various events, projects, and activities. And as the student committee of MLDA, our mission is to execute and plan those events and workshops. And we do so through the help of our state-of-the-art faculty resources and technical support to facilitate your learning journey in MLDA. That's basically MLDA. So now I can pass my time back to Sean to continue with the workshop. Sean, please.
Thank you, Andrew. Okay, so before we start with the workshop, I'd like to talk a little bit about what we're going to do today. So first, I'll be introducing the idea of the workshop, and I'll be describing the overall general idea of ROS itself. Then we'll be splitting into our breakout rooms where we have facilitators, which will help guide you along as well. So the flow will be, I will go through once in the main meeting, then we'll split into the breakout rooms for everybody to try. And if there's any problems or questions, feel free to ask your facilitators and they will help you out. Thank you. Okay, so what is ROS? Before I talk about ROS, I would like to ask a question. How would you build a self-driving car? Well, normally we will need the wheels and the motor controller. We'll need some sort of navigation for a self-driving car. And we'll need sensors in order to detect the roads, maybe detect where we are, perhaps a GPS, maybe some image recognition as well. And all of this is traditionally written in one code. You can have multiple classes, multiple header files, multiple linking and all that. But overall, it's one code and it's quite linear. And you write in either Python or C++ only normally. You can write in other languages, but the general idea is we generally write in one language. But with ROS, you can write in either Python or C++ at the same time. And let me emphasize a little bit more about this. So in ROS, each of the individual components can actually be written in a code. So we can have 7 or 8 different codes. Maybe we can have 3 of them in Python. We can have the other 5 in C++. And all of them will work together at the same time. And all of them can communicate with each other. So this is the main idea of ROS. Multiple codes working together at the same time. And they are able to communicate to each other. So some of the misconception of ROS is that it's an Arduino, a microcontroller like an Arduino. It's maybe a small computer like a Raspberry Pi, or it's an actual operating system such as macOS or Windows. But it's not true. This is not ROS. ROS is mostly done in the terminal of Ubuntu. This is where we normally do ROS in. And ROS can actually connect to microcontrollers such as Arduino. It can connect to industry-grade sensors, such as this LiDAR, and it can connect to multiple cameras and other sensors as well. And we can also incorporate really popular libraries such as TensorFlow or OpenCV and use it in conjunction with ROS. So perhaps one person would like to use TensorFlow to do the image recognition or maybe a path planner, and another person is actually getting the image from OpenCV and some cameras. Well, everybody can do it together at the same time. And that is another idea of ROS. It's available in the Linux system. You can write in either Python or C++. And since you can write in either Python or C++, you can incorporate traditional libraries into your project. So ROS is also traditionally done in Ubuntu, which is a Linux-based system, which is something of what we're going to be doing today as well. Okay, So what makes ROS special? I have talked a lot about what is ROS and a little bit of the idea of ROS. I hope everybody can get the idea of a bit, but that's just the idea of ROS. What is it about ROS that makes it special? Well, the first key is that it's open source. So it's readily available online and everybody can readily access it. It has a lot of pre-built packages for components, sensors, navigation, which means that a lot of people have actually worked on these codes before and it's available online. So let's say you buy a certain sensor. Well, all you need to do maybe is contact the manufacturer to see whether they have this code already. And if they do, you can incorporate it into your project seamlessly. And another key feature about ROS is that multiple people can work on multiple parts at the same time. So it's a very modular so-called platform that we can use. I would like to reiterate on my self-driving car example. So in a basic self-driving car, we have three components. One is the wheels, the motor controller, and then the second one is the navigation, and maybe the third is the sensors. So let's say we have three people and they want to work on it on this self-driving car together. Well, normally you have to write the wheel code separately, then write the sensor code, then write the camera code, and then after that, use pointers or classes to point to everything together. But with ROS, right, everybody can work on their part at the same time. And to combine it together, everybody just needs to agree on a certain topic or message, which I will go through later. So by standardizing and streamlining the way we communicate, the codes communicate in ROS, it actually speeds up development time. Therefore, multiple people can work on it at the same time. And since multiple people can work at it at the same time, it actually inspired a very, very large community. And since we have a large community, in order to make development time faster, they standardize and streamline a lot of the popular ways that code will talk to each other. Okay, these are some examples of what we can do with ROS. The first one is the self-driving car. In the top right, you can see it's a drone that's navigating by a camera. And below is a social robot. So for example, maybe you're at a movie theater or a shopping center and you have no idea where to get to. You can interact with the robot and the robot can lead you to the store or maybe the utility that you're looking for. Okay, so this is one example of ROS in action. So as you can see, in the bottom left of this video is actually a car driving around a neighborhood and it's actually detecting edges on the images. And in the other three screens, is actually the map that's being created live. Another example of ROS in action. So robots can autonomously move to different locations and pick up maybe some payload, some cargo, and move off. Yeah, so these are some examples of ROS in action. Okay, so now I would like to talk about where is ROS located in. Well, imagine this big box is your computer or your Raspberry Pi, the hardware itself. And then within it, there's your operating system, the Linux, Windows, or Mac OS. Then inside the operating system is actually where ROS is located. And where is your code located or where is your codes talking to each other in? Well, it's actually inside ROS. Okay. So how do the codes talk to each other? Well, I would like to emphasize heavily on two words, and these two words forms the general backbone of ROS. The first is nodes and the second is topics. So first of all, what is topics? Well, topics are actually the messages that's being sent by your codes. So what's in a topic? First, there's the name of the topic. Then the topic must have a format, such as whether it's a string, whether it's an image, whether it's a matrix. Then it must have the content of the topic, which is the actual string that you're being sent, the actual data. And it must have a sender and a receiver. In ROS, we call the sender and receiver publisher and subscriber. So this is an example of a topic which we will actually try during the hands-on later. So the topic here in this case is called chatter. It's a string. There are a publisher, which is the talker, and there's a subscriber, which is called a listener. And inside the topic, you can see the data, the hello world, and some integer. Okay, so what are nodes? Well, these are the nodes. A node is basically, in essence, each component of your code. Each component of the overall system, sorry, can form a node, and each of the node can do like specific things. Okay, so this is a real example of a node and topic in action, which we will try later as well. The talker is a publisher, and the listener is a subscriber. And the topic in this case is called chatter. Okay, so there's one other thing I want to emphasize a little bit about. It's actually called ROS master. Well, ROS master is actually uh, just a server in order for the nodes to communicate to each other. It just activates a server. And the codes are communicating using TCP IP or actually TCP ROS. So in gist, ROS master just opens a server and it enables our nodes to start talking to each other. And in order to activate ROS master, we just type ROS call in a terminal. So where is ROS master? ROS master is actually the overall framework which supports all the codes and topics. This is how ROS master looks like. Okay, now we move to the hands-on part. The hands-on part will be broken up into two main features. The first one will be I will be demoing step by step here, and then we will go into our breakout rooms where you will try yourselves. And if there's any problems, feel free to help. Feel free to ask the facilitator in your breakout room. Okay, so we'll be using this platform, the ROS construct. We will need to create an account. My colleague is sending out the link for the website in the chat. And we'll be searching for a ROS check, which I will emphasize a little bit about later. Okay, actually, I will go through this hands-on. So maybe can I ask everybody to take some time, maybe about 10 minutes, to just create an account in the construct before I will continue. Thank you. I will continue the workshop in about 7:22-ish, like that. Yeah, so everybody can now feel free to drop some messages in the chat if you have any queries. And in the meantime, just create an account and just head over to here. You should see something similar to this. No, the recording will be posted to our YouTube channel, MLDA at EEE at NTU. With regards to all the materials, we will try to share it to you guys as well. ROS1 is actually available in Windows, but you have to use something called Linux in Windows. Is it possible to do everything in a Docker? I would say no, because a lot of the things you need to connect out to the sensors will have like a lot of problems. Yeah. Today we will be using this virtual simulator, the ROS construct. This is basically Linux plus Ubuntu plus VS Code plus ROS already prepared for us here. So ROS is the original. It's traditionally used it has been used for quite a while, and a lot of the actually industry is using ROS currently. But ROS 2 is actually a new and up and coming thing. So ROS is more or less stable enough, and like a lot is quite well known. But ROS 2 is actually up and coming. Most of the idea of ROS is moved to ROS 2, but ROS 2 has new ways of like uh doing what we're gonna do today. And it has a lot of other features as well. But what we do today can be done in ROS 2 as well. I would recommend to it depends on what you're aiming for. If it's just a hobby project, I would recommend ROS because number one, it's quite stable. Number two, it has a lot of really pre-made packages. And number three, like a lot of the companies with their sensors and their GPS and all that, they made their codes for ROS. ROS 2 is relatively new compared to ROS. So for a beginner to dip their toes in the idea of ROS, I would recommend the ROS one, this ROS. And what we'll be doing today is actually the original ROS. No worries. Does anybody have any problems coming to this website, creating a free account and seeing this page? If not, we will start. I will continue in about another 2 minutes. Okay, we will now continue. So what I would highly recommend is first, I will now continue, yeah. So what I would highly recommend now is just take a look at what I'm doing. It doesn't matter if you don't get it because I will be going a little bit fast. But when we go into our breakout room, feel free to then you feel free to go back to your own construct and ask your facilitators like what to do. Yeah. So I will go through the general idea here first of what to do, and then after that we will everybody can go into their breakout rooms. Okay, so the first thing we're going to do is search for a pre-made project. So if you search MLDA, you should see these. These are actually made by us. All of them is the same. So you click on it. For me, it says run, but for everybody else, you should see something like this. So it'll say fork. So just click fork and just confirm it. And then after that, you just go into your ROS jack and you should be able to see it. Similar to this. Just press fork and just press confirm. And then you should be inside your ROS jack. So we have multiple other things. So inside After this, you can just press run, and then it will just open up everything. So this version of ROS we are using today is actually ROS Kinetic. The current ROS available is ROS Noetic, which is I would say is close to the end of the ROS 1. ROS 2 is actually a bit different from these. Yeah. ROS Kinetic has been it's 3 or 4 generations back. ROS Noetic is the current one towards the end, which is the newest one. By end, I mean the end of the ROS line, not the ROS end of ROS 1 itself. The end of the what is out for ROS, not the end of ROS 1. Okay, so when you open it up, this is what you should see. We are just going to close this because we are not using Jupyter Notebook. We will be using this below, web shell, which is actually your terminal inside your Linux, and this code editor, which is the VS Code, similar to VS Code, which is the IDE. Okay, so just a hint, just a tip. If you open up something called Kekin Workspace, which is where we're going to be putting in all our codes, just delete this. Actually, no need to delete. It's not too much trouble actually. Okay. So we'll also be distributing out ROS cheat sheet. So this is a lot of the basic commands and the basic tools that we'll be sharing. I just created just a simple cheat sheet for everybody to use. Okay, so the first thing we're going to do in ROS is actually how to create a package. So in order to create a package with a ROS package, we will use this command, which is called Kekin create package, followed by the package name and what it depends on. So in this case, I have an example. I'm just going to copy it and just paste it in my, but first I need to go to where I want to create the package. So we'll create the package inside our Kekin workspace, inside our SRC folder. So I use cd to where is it, and then I will paste the code. So we just press enter, and then you can see there's a new package that has been created here. So after that, now that we have created our package, let's add in some codes inside our package. So we will be going to the ROS workshop, the ROS wiki itself. So just copy this, going here. Okay, so all of this has been done already. Actually, we're interested in the code. So this is the C++ version of the code. Later, we'll see actually, right, both the Python code and the C++ code can communicate to each other, even though they are both written in different languages. So for now, we'll just copy the code. So this is the first code. Then I will just create a new file. I will call it docker.cpp. And inside here, I will just paste the code and save. Same thing, I will do the same for the listener, which is the what we are using to subscribe to it. After I create these two, I'll just talk a little bit about what they are, but to explain the whole code is beyond the scope of today's workshop. Okay, so new file. This one we'll call this listener.cpp. And we'll paste and save. So Docker is actually, in this code called Docker, what is it doing is actually, it has a count, and then we're just increasing the count every time, and then we're just publishing it under something called chatter in a string. So inside our string, we're actually putting in the data, hello world, and then for our count. Then after that, we'll increase the count. So this is the very, very basic publishing code, which we'll send out. Then as for listener, same thing, it's just subscribing to chatter. And then when it receives a message under chatter, it will execute this function called chatter callback. And then chatter callback is basically just printing what it sees inside the message. Okay, and we will do the same for the C++, for the Python version of the code. So we just go down. This is the C++ and this is the Python. Same thing, I'll just copy this. I'll create a new file. I'll call it talker. This time it's a Python file, so we call it talker.py. Paste and we'll save. Same thing, we'll do the same for listener. We'll save. So the talker in the Python and the talker in the C++ is exactly the same. It does pretty much the same thing. So there's one more thing I want to highlight. So in, as you know, C++ is actually a compiled language, but Python is an interpreted language. So we need to let our system itself know what is what. So I would like to talk about the Python one first. So if we just go inside where we have the packages, and then I use a command ls, which is list, we will see what's inside our src folder, inside our code, which is basically listener, talker, in the both languages. Then right, you can see the Python files are actually in white, which means that we know it exists, but we don't know it's executable. So in order to change the permissions to let Linux or Ubuntu or ROS know that these files can be run, we need to do chmod +x talker.py and listener.py. So if we list again, you can see they are now green and they are now runnable. The last thing we do before we go into our breakout rooms in order to create these codes first is to let ROS know that the listener and the talker in C++ actually runnable as well. In order to do that, we need to go into the CMake list of our package, go all the way down and add in these 4 lines. Basically, these 4 lines so-called compile the package, the C++ files. And in order to run it, we have to cd well, cat kin, then cat kin make. So once we run this, it will slowly build the packages. So there's some errors. I need to delete my old package. Yep. Okay. So there was a conflict of the package because I was testing the workshop. Yeah. So if you guys run into error, please delete the test package test code below. But basically, if you see this 70 linking of the talker and linking of the listener, means we're good to go. Okay. So now we'll break out into our breakout rooms and feel free to try all the steps. The ROS cheat sheet will be sent out again just before we open the breakout rooms. Okay. So basically what we have, I'll just summarize what we did so far. It's all we did was create our package and put in both the talker and listener in both files, both language, the Python and the C++. And then we have told ROS and Linux that these are ready to go. These could be run. So we will try for about 15 to 20 minutes, about 7:50. Everybody will come back into this main meeting, and then we will show how to run the codes along with some tools that we can use in order to use the code. Okay. Okay, hi guys, welcome back. So now that we have created the codes, let's talk about how to run it and then some of the tools we can use in order to see some of the topics and notes in action. Okay, this is actually all in the slides, but I'm just gonna go through without the slides. Yeah. So let's go through the things. Okay, so first thing, in order to run anything in ROS, we need the ROS master to be up. So in order to activate it, we just do ROS call. As you can see, in this terminal, our ROS call has started. We can see this started call service, which means our ROS master ROS call is up and running. So in order to run the codes, we will need a new terminal. And the command to run a code will be ROS run. Where have we created our code? So in our case, it's a new package and Docker. So as you can see, Docker has started running and it's printing, the code for Docker is actually printing hello world. So let's run a listener. But for now, I'm going to run actually the Python version of listener. So ROS run, same place, new package, but this time listener.py. So this is actually the Python version of listener. And this, in essence, is the very basic of how we will run a code in ROS. As you can see, the thing is sending hello world and it's saying I heard hello world. If I stop the Docker by using Control C, you can see it has stopped, nothing is being sent. But if I simply run it again, you can see it's restarted back at 1, 2, all the way to 30 something. So this is how we run our codes in ROS. So the very first tool I'm going to teach now next is actually something called ROS topic list. So ROS topic list is a command that shows everything that's being sent around, being published in the ROS environment. So here you can see we have chatter, which is what is being sent by our Docker, and we have something called ROS out and ROS AGG. ROS out and ROS AGG is actually default topics that's being sent by the ROS master. So these two are default and they don't do very much. But chatter is the topic that's being created by our two codes. So now I want to have some more information about chatter. So in order to do it, the next tool I'm going to teach is ROS topic info slash chatter. So with ROS topic info chatter, I can see all the information about chatter that's going on in the ROS system. So chatter is the topic, it's a string. There's one publisher with it. The publisher is called Docker, and there's one listener to it. So the Python version of listener is actually listener and then this random numbers behind it. Okay, next is, let's say I want to see what's inside the topic. I will use ROS topic echo chatter. So with this command, I can see what's being published inside the chatter. Same thing, in order to stop, Control C on my keyboard and it stops. Okay. Next is the last tool I want to teach for now is ROS topic hertz chatter. So ROS topic hertz chatter is actually just seeing how fast each of the topics are being published. It's quite useful for things like computer vision and cameras because they run on frame rates. And like maybe if you want to see if maybe let's say you have some instruments that need to send the data very fast, you need to see whether it's actually achieving the so-called the frequency or the speed. We can use ROS topic hertz as well. Okay, next, now we have seen like all the codes, right, and all that, and all the topics and all that, right? But how do we visually see how our nodes and our topics are connected? Well, we'll need something called a graphical tool. In this case, but actually in the normal Linux, it's just a simple computer screen. And then I will use something called RQT. So RQT graph opens up, actually it's like similar to a mind map. Similar to a mind map, as you can see. Let me zoom out a little bit. Okay, yeah. So this is so-called like how our nodes are being connected in ROS itself. You can see that we have a talker and we have a listener, and there's something being sent called chatter. Okay, let's see. And finally, the last thing I want to go through for now is something called a launch file. So as you can see, right, I have to open 4 terminals just to run a simple talker and listener. Imagine if we had to do a autonomous vehicle, how many codes do I have to run at the same time? Well, in order to run multiple codes at once, I'll use something called a launch file. So I'll just simply close all the terminal. Just close this one as well. Close this. Close, even close the ROS call. Okay, so in the cheat sheet, I have already an example of a launch file I created before. Basically, we're just going to copy this and I'll explain a little bit. Okay. So inside my package, I'm going to create a new file. I'm going to call it test launch. Actually, I'm not going to call it test launch. I'm just going to call it test. Okay. And inside test launch, I'll just paste my launch file. And save it. Okay, so basically this launch file is launching from the node new package, run talker.py as talker, listener.py as listener from the new package. So in order to run it, we just use a new terminal. So with a single terminal, I'm going to run both codes at the same time. So the command is ROS launch new package test.launch. So basically, ROS launch from where, what. And with this one command, I run my ROS call and my talker and listener at the same time. So if I just simply use RQT graph again, in my graphical tool, we can see that it's all being connected as well. Or it's all being launched and all being connected at the same time. Okay, we'll now go back into our breakout rooms in order for us to try.
Hi guys, can you join back to your respective breakout rooms? It's in the options menu. Thanks.
Okay, hi guys. So now we have the general idea of how ROS works and what are topics and what are nodes. The last thing we're going to do today is actually we're going to control our first robot. Okay, so actually, ROS itself already has pre-built a few robots internally. So we're going to use one of them today. The first one, so in order to run the robot, we just we will run uh these two line of code in two different terminals. So the first one is to run the total sim node. Then as you can see in our graphical interface, we have a total robot that has appeared. Okay, and then this is just a robot. So we need to control the robot. In order to do that, we're going to use our keyboard. So this is how we're going to control. So using a few terminals, this one has opened up the robot, and this one is now able to control our robot. So if I press my arrow keys, if you can see, my robot is actually moving around, following my arrow keys. Try to draw a nice little square, but my drawing sucks. So yeah, we have some weird shapes. So the last thing I want to show today is actually the RQT graph. So I'm just going to refresh it. And then as you can see, I didn't close my toggle and listener, but you can see two new nodes has been added. This is my teleop, which is my keyboard, and my total sim, which is my robot. And it's being sent the total command bell, which is basically the movement command. And if we want to see what's inside the topic, well, we can use our tools, all the tools that we have learned previously, like ROS topic, echo, slash, and we do tap, we can actually see all the topics that's being sent out in the ROS system. So the one that we're interested in is actually total one command file. As you can see, currently there's nothing, but let me position the things nicely. But the instant I press my keyboard, things start to appear and the robot start to move. So this is the basic general idea of how maybe we will make a self-driving vehicle. We'll have our navigation system send a topic to our robot. And generally, in the industry, we use something called command bell, which is the linear XYZ velocity and the angular rotation. Okay, we will now go back to our breakout rooms, another 20 minutes or so. Then I'll wrap up the workshops for everybody to try and troubleshoot the rest of the things with your facilitators. Everybody, please join your breakout rooms. All right, guys. I just want to say that I hope everybody has learned something new here, tried some of the raw stuff. I want to close off by telling you guys like some of the differences between the simulating and what other things we had to do to set up ROS normally. So normally you download ROS, it will be at the ROS website. Just follow the instructions. Some differences. So some of the things that we have used today is a lot of Catkin. Catkin is actually just a Python tool in order to set up all the packages. So we need to install it. We need to create our own workspace. We need to edit something called a bash RC to source the ROS and the Catkin workspace. Basically, this lets this like so-called enables the workspace. If you don't edit the bash RC file, you have to source your Catkin workspace and your ROS every time you need to use it, because you can actually have multiple version of ROS, multiple workspaces. You just need to source it to let ROS know where to look for. Okay, and thank you guys so much. Hope you guys enjoyed everything. Before we do a feedback, can we have a group photo taking session? Can I invite everybody to on their cameras if you guys feel comfortable? Okay, if not, we will end the meeting here. Thank you. Bye bye.